Okay, excellent. So, welcome. I'm going to be talking about some of the new kernel features that appeared in 2024 and in 2025 so far, and all that are all that are expected later this year, with particular emphasis on embedded systems. A few words about myself. I've been a Linux kernel developer since around 2007. I've been working mostly on embedded systems since 2014 and at Mind since 2020. Outside of work, I'm also on the Debian kernel team working on packaging and configuring both the kernel itself and some of the closely related packages that support the kernel. I'll start with support for new systems on chip. I think it's really important to have support for embedded hardware upstream, because without that, you can get stuck on a vendor branch that was created maybe a year or more before the chip was even released, and so you don't get to take advantage of new features, and you may not even get really important security fixes. So most of this new support is for devices with ARM CPUs, and the vast majority of these now are 64-bit. There were a few new 32-bit SoCs added. I've looked at the device trees that were added. I don't know how well all of the different devices on these are supported by drivers. So we've had new chips from Aeroha, AMD, Amlogic, Blaze, the Broadcom SoC that's in the Raspberry Pi 5, from MediaTek, Microchip, NXP, a whole lot of different chips from Qualcomm, NSS, Rockchip, Samsung, Exynos, STMicro, TI, and Unisoc. And for other architectures, there are actually some new MIPS SoCs from Mobileye, RISC-V chips from Softgo and SpaceMIT, and on x86, AMD and Intel have been adding support for the new chips that they launched in 2024 and 25. So aside from that hardware, my first topic is real-time support. Some background for that. For a long time, Linux has offered a compile time trade-off between throughput and latency. Preemption of user space code is always possible when there's a higher priority task, or when the user space task has exhausted its time slice. But preempting kernel code is a bit different, because you have to be concerned with things like locks held by the kernel. So your options have been preempt none, which maximizes throughput at the cost of latency, preempt, which minimizes latency at the cost of throughput, and the centrist compromise of preempt voluntary. According to the kernel configuration help text, these are suitable for servers, low latency desktops, and desktops respectively. I think this advice is a bit out of date, because a whole lot of server applications also need low latency. And you'll notice there's no recommendation for embedded systems there. You've got to work it out for yourself. Now, hard real-time systems need a guaranteed maximum latency for response to certain inputs, or alternatively, guaranteed CPU bandwidth for particular tasks. And none of these options can provide those guarantees. So starting in 2005, there's been a patch set called Preempt RT, or alternatively Linux RT, and that aimed to support real-time systems, adding this fourth option, config preempt RT, which makes the kernel fully preemptible. Or to be precise, the the sections of kernel code that aren't preemptible are reduced to the point where you can actually start to make guarantees about how long they can take. Unfortunately, this patch set included a lot of changes to a lot of different kernel subsystems. It turns out that some of those changes are beneficial to all configurations, not just real time, and so those changes were relatively easily accepted by upstream developers. Others were harder to justify and potentially would cause regressions for other configurations, and so a lot of time is spent reworking those into a shape where they would be acceptable for upstream. Finally, Linux 6.12 has included almost all of the pieces that were remaining at that point. And so it's now possible to select preempt RT on several different architectures. ARM64, Long Arch, RISC-V, and x86 support it. With a few extra patches that haven't yet gone upstream, you can also use it on 32-bit ARM and on PowerPC. So we can say now that upstream Linux is suitable for real-time applications, but with some caveats. Firstly, system firmware, particularly on x86, where you have the BIOS, system firmware may be able to interrupt the operating system, and that can add unknown latency. Typically, you don't have access to the source of that system firmware, and it's going to be quite hard to reason about and to guarantee anything about that. Applications, of course, need to be pretty careful to actually achieve real-time behavior. They need to log all of their memory to prevent it from being swapped. They need to be pretty careful about what I/O they do. As I understand it, access to I/O devices that they have exclusive control over is okay, but block device I/O or file system I/O is out of the question. And the worst case latency on Linux is still going to be probably many times higher than if you were using a purpose-built real-time operating system. But you get the benefits of relatively easy integration between your real-time tasks and other tasks that can make full use of the Linux API and user space. Our next topic is security hardening. Recent legislation, such as particularly the Cyber Resilience Act in the EU, is putting responsibility for security flaws firmly with the vendors of embedded systems. So it will in future be mandatory to provide security updates for bugs that are being exploited for a reasonable time, a reasonable lifetime of an embedded system. So every security flaw that's either excluded because the code simply isn't built, or effectively mitigated, then won't be exploitable, and it can't require an urgent security update that's disruptive to development and costs a lot of time and money. The kernel self-protection project was started, I think, about 10 years ago now, in an effort to harden the kernel that is mitigating security flaws and to support a more secure user space. Some of the things that does are to fix or remove insecure kernel APIs. It mitigates common classes of bugs that often have a security impact, such as use after free or buffer overrun. And this already makes it pretty much impossible to inject new code into the kernel. Any attack on the kernel has to rely on changing data in the kernel that has that's security relevant, or for example, overwriting the stack, overwriting return addresses on the kernel stack to take advantage of to change the kernel, to change control flow in the kernel, which is called return-oriented programming, or ROP. So some of the new mitigations that have appeared in 2024 and 25. We have two mitigations for heap use after free vulnerabilities that can result in that can allow a type confusion attack. With use after free, you can have one part of the kernel that originally allocated an object, considering it to be still that type of object, while meanwhile it's been incorrectly freed, and then the same memory has been reallocated for a different purpose. And so you have different sections of kernel code that disagree about what type this memory is, and that confusion is exploitable. So your options are: you have a compile time option that randomizes the kmalloc caches that are used in heap management. That works globally, but it's probabilistic. It can't guarantee to prevent these sorts of attacks. It makes them less likely to succeed, which means the attack is more likely to crash the kernel. But it doesn't guarantee that such bugs are not exploitable. As an alternative, or in parallel with that, you also have the dedicated slab bucket allocator that can fully mitigate this type of attack. But it's a new kernel API, so it will require code changes all over the kernel to take advantage of it. For user space, you have normally all of your executable code will be mapped read and executable, but not writable. And all of your writable memory will be marked read write, but not executable. And that provide the same sort of protections against replacement of code that we already have in the kernel. Unfortunately, there's also an API within the proc file system, proc process ID memory, proc process ID mem, which allows access to a processor's virtual memory space from outside that process. That's quite useful for debugging, and I know that some language runtimes use that for just-in-time compilation. And through that API, it's possible to write to memory that is marked read-only within the process itself. You now have a compile time option and/or boot time option that can disable this insecure API. But because there are legitimate uses of it, this is not being done by default. But for an embedded system, very likely you would be able to decide that that's not something you need, and you can disable writing through that API. There's a new system called mseal. Comes from, I think, the Chrome OS developers, and that allows user space to lock down the configuration of some memory mappings that would prevent accidentally changing memory mappings to be both readable and to be both writable and executable. Which again would be the first step to replacing code in a process. So yes, so with MSeal you can prevent such accidents or prevent an attacker from doing that using return-oriented programming. And finally, there's support for shadow stacks in user space. Historically, the stack contains both local variables allocated in functions and the return addresses that keep track of where to return to when a function completes. Because those are intermixed, it's possible that an out-of-bounds write to a stack variable can overwrite the return address. And this is used by attackers, as I previously mentioned, for return-oriented programming. Shadow stacks are a new feature supported on several different architectures that add a secondary stack that's only used for return addresses. When a function returns, then the CPU will verify that the address on the regular stack and the shadow stack match, and if they don't, it will result in an exception that typically kills the programming. So support for shadow stacks needs compiler changes. Those I think have already been in place for some time. It needs changes in kernel, and of course it needs a CPU that supports this extension. The kernel support has now landed for ARM64, RISC-V, and x86. So that's definitely something that's worth turning on if your hardware supports it. And then for configuration, there's now a configuration fragment included in the upstream source that enables a bunch of security hardening options. You can run make hardening.config to apply these changes on top of your existing configuration. That's not everything. It's a pretty conservative set of options. There are other compile time options that may have a greater performance impact or be incompatible with some user space applications. It also doesn't include some configuration settings that are only available at runtime. There's a separate. There are some third-party projects that provide a longer list of configuration changes to check against. And now, everyone's favorite language, Rust. I think this kind of ties into the previous topic of security hardening. Rust is, I think I can no longer say it's really a new programming language. It's been in development since 2006, and version 1.0 came out in 2015, so it'll be celebrating its 10th birthday this year. It's a systems programming language suitable for the same sort of applications as C and C++, and some other modern competitors like Zig. Very much unlike C, it has a strong type system, and its major innovation, the borrow checker. These help to prevent many of the classes that often result in security flaws in C and C++ code. For example, data races, where you have the same data being accessed from different threads in ways that results in inconsistency. Use after free bugs, which I discussed before, out of bounds access. Those are more or less impossible, with the caveat that it's possible to write explicitly unsafe code in Rust that relaxes some of those checks. The performance is, as I understand it, pretty much comparable to C. You don't have garbage collection or other runtime overheads. The language is quite a bit more complex than C. It's going to be harder to learn. Maybe not harder to learn than how to use C safely. Comparing with C++, I think I haven't kept up to date with all the latest changes to C++ or Rust, but I think they're roughly on par. Support for Rust in distributions is somewhat less mature, so you may not yet be able to rely on having a recent Rust compiler on your build host or in your embedded system distribution, whether that's Buildroot or Yocto. Both of those do have packages for Rust, but they may not be as up to date as you'd like. So for Linux, there's a Rust for Linux project that's been running for about 5 years now. That adds support for using Rust in the Linux kernel. That includes support in the kernel's build system, adding safe APIs for Rust that work on top of the existing kernel APIs designed for C. They're called bindings. And that's also making changes to the Rust language and its standard library to support the needs of the kernel. The changes to the kernel started being merged upstream in Linux 6.1 in 2022. What went in initially wasn't enough to be useful. You couldn't start building drivers with it, and there was some progress on fundamental APIs in 2023, but it was quite limited. Since then, we've had somewhat faster updates. In 6.7, bindings for work queue and work item APIs. 6.8, bindings for writing PHY drivers for Ethernet. Support for building on Long Arch. Initially, there was only support for building on x86. 6.9 added support for ARM64. 6.10, RISC-V. 6.11 added bindings for writing block drivers, loading firmware, access to user memory, user space memory, and some of the page allocator APIs. 6.13 added support for some of the file system APIs and writing MISC device drivers, and for adding trace points inside Rust code. And 6.14, which should come out in a few weeks, adds bindings for writing PCI and platform drivers. And then the release after that, 6.15, will very likely include bindings for the DMA API, despite the recent very public disputes over inclusion of those. And later in 2012, I hope to see some real drivers going upstream rather than just samples. And this should start to be an option for any new drivers you need for your embedded systems. So, yeah, I see Rust as being having there's a lot more to learn about the language, but once you've got that down, it should make it quicker to write a driver that is correct and safe to use. The next topic is SCEDX, which is a change to the Linux task scheduler. The default behavior of the task scheduler is it's a compromise. It works pretty well for most applications. It's not optimal for every application. Maybe not for any single application. There are multiple different scheduling classes available which offer different behavior, including real-time and background task behavior. It's not really modular, though. You can't just drop in a new scheduler as a kernel module, for example. In the past, some developers therefore forked the kernel to make their changes to the scheduler. Most famously, Concolivas's BFS and later New QSS. And various SoC vendors have tweaked the scheduler, mostly to improve interactive behavior on Android. But now we have the SCEDX class, which, as I understand it, replaces the SCED normal when it's active, and that allows some customization of the behavior, particularly in picking the next task to run. All the rules for that are defined using BPF, which is now the general purpose kernel extension language, or extension bytecode format rather. So no changes to the kernel code are actually required at all if you want to experiment with that, or even in production. So with that, your custom scheduler should ideally continue working even after a major update to the kernel. And we have some minor topics that I found that will be useful for some embedded systems. Some changes to thermal notifications to user space. Thermal management is well, it's critical. If you don't handle the SoC or other components going over temperature, that can result in damage to the system, potentially safety issues as your hardware catches fire. The kernel has long had thermal management, and in some cases you also have system firmware that's doing thermal management and will shut things down if they get really out of hand. But if you want a more complex policy to, for example, gracefully shut down low priority tasks, or just scale back what you're doing, that needs to be implemented in user space. So the kernel thermal devices have provided notifications to the user space when reaching trip points that may be configured in the device tree. Typically, you now have an API for configuring an additional threshold for notifications at an arbitrary temperature, so that would allow you to implement this more graceful handling of temperature increases rather than doing a sudden shutdown or killing tasks once the temperature gets really high. Now the GPIB, General Purpose Interface Bus, also known as IEEE 488. This is a really old bus designed at HP in the 1960s for connecting their test and measurement equipment together. It later got standardized and has been implemented by multiple vendors. And that's standard, I think, continued being extended up into the 2000s. I don't think this is likely to be used in Linux-based embedded systems, but this may be useful for automating and controlling hardware test benches. There have been Linux drivers for controlling hosted adapters that attach to GPIB for those can plug into their PCI or USB buses. They've been developed out of tree for quite a long time. The project is on SourceForge, which perhaps gives you an idea of how old it is. It also includes drivers for ISA and PCMCIA adapters, which I guess aren't very useful anymore. That's now included upstream in the staging directory, so that's something that's hopefully going to be kept up to date with the kernel, and it's more likely to be available in distributions now. So that's all I have. I have looks like we have a fair amount of time now for questions. If anyone has those.
Hello, Ben. I have a question.
Hi, Olivier.
Is it possible to use at the same time preempt RT and shed ext?
I think so, yes. I don't know specifically. I think SCEDEX would allow you to change the behavior for regular non-real-time tasks, while the your real-time tasks use the existing hard-coded schedulers. But I'm not certain about that.
Okay, thanks.
Okay, a question from Christophe Dutoin about the Rust infrastructure. Aren't there some real drivers already? There are, out of tree. Those rely on some bindings and possibly other changes that are not yet upstream. So my hope is that those will go upstream in 2025. But there may still be blockers that I'm not aware of.
I have a question too.
Okay.
It's also about ShedXT. So BPF is a pretty restrictive language by nature. What is the scope of the customization we can hope to achieve with the BPF extensions for ShedXT?
I didn't look too deeply into that, but as I understand it, the main thing that you can do with it is you can choose what is the next task when a task either sleeps or reaches the end of its time slice. So you can effectively change the prioritization of tasks in a flexible way.
Okay, thank you. I was curious about it.
Hugo's asking about the Debian bug squashing event. That's I have been busy working on this talk, but I will try to get that finalized this week. Okay, another question from Christoph about preempt RT. You mentioned user space applications should be careful with I/O. Would you have a concrete example to share here? I'm afraid not. I personally haven't worked on Linux real-time applications. But what I do know is that as things like block schedulers and network schedulers are not real-time aware, so you don't get the same sort of real-time guarantees if you're using those if you're sharing block and network devices. Any more questions?
I think we can close here.
Okay.
Thanks everyone for tuning in.
Yep, and thank you for the well-considered questions.
Hugo.
Cool.
You want to say something, Hugo?
No, sorry. I mistakenly just wanted to give some claps to Ben for a very exciting and interesting talk. Thank you.
You're welcome. All right then.
Right.
Goodbye.
Thanks. Bye-bye.
Bye.
Good night. Thank you.